Hello everyone, welcome to another video. In this one we will be building RAG. So RAG is a pretty known concept in AI engineering domain. It stands for Retrieval-Augmented Generation, and in this section we will be building a special or a specification of RAG, which is also called self-RAG, which is a self-retrieval-augmented generation, and we'll be building it from scratch using the LangChain framework. And what I would like to cover is this will be the high level design which we'll be covering. A user will give a question, and when a question is given to the agent will gonna generate the answers. But along with generating the answer, the self RAG has a capability of self reflection, meaning it can understand whether the answer generated was correct or not, or was relevant or not. Apart from that, it can also decide whether the model or whether the model embedded in the workflow has hallucinated or not. So suppose uh, my RAG workflow has a large language model in the heart of it and it hallucinated for some reason, then this self RAG workflow will be able to understand that and will gonna notify the user, and instead of giving a wrong answer, it will gonna notify the user that hey, the model has hallucinated and you should try again, or you should fix something in your workflow so that it doesn't do that, right? Apart from that, we'll also check whether since in a RAG, in a retrieval augmented generation workflow, we provide external knowledge base to the model so that they can be grounded on that, right? So it can be any private information or any external information which the model does not have currently. And what the workflow does is that from that knowledge base, it picks the relevant document depending upon the question that the user has asked. So the self RAG has the capability of understanding whether the document was relevant or not, because it can happen that the large language model can extract a lot of documents from the knowledge base depending upon the question, and some of the documents might not be that relevant. So it would be helpful to perform a second filter on which we basically filter out the irrelevant documents so that we have a solid knowledge base on which the large language model can provide us an efficient answer, right? So that is the high level idea, that is what we are building. So we are building a self RAG here. It is iteration on top of RAG where we introduced hallucination grader, answer grading, and document relevancy, and we're gonna see in action what everything is. Apart from that, this is picked from a research paper. I have added the screenshot here. It's the title of the research paper is Self RAG: Learning to Retrieve, Generate, and Critique through Self-Reflection. And this is what we'll be building. I'll also be walking you through this paper as well to understand what has been covered in the paper and how what we are building here in this video is relevant to this paper. So one of the intuition to build this project came from LangChain as well. So they have the implementation of self-RAG done in one of their open repository, and this is the link. I have opened this repository actually, and they have implemented self-RAG. The link to the paper which I discussed earlier is also here, which I'll be anyways walking you through in the session going ahead. And yeah, this is the repo. You can check it out as well. We're gonna build this and we're gonna discuss how you can build this from scratch. This is what they have done. I will build a simplified version of this where we'll not perform the looping, so we'll not read out the question, because I want to reduce the case of multiple LLM calls and I want some control, some humans in the loop. So we're gonna, instead of looping back to the user, we're gonna tell the user that hey, whether your model hallucinated, or whether the answer was not relevant to the question, or whether the document is not relevant. In all these cases, we're gonna tell the user and we're gonna let the user take the step that what they have to do next, or how they want to debug their workflow. So that's what we'll be doing next. So now let's come back to our notebook, and here we are building self-RAG from scratch. So I'll gonna first move on to the problem statement so that we are clear on what we are building and why we are building that. So I have already explained that RAG is retrieval augmented generation, where it takes some knowledge base so that it can ground the large language model on those documents, so that in future when you want to ask questions related to those documents, then your model can respond, right? And that is RAG. But in RAG, we have introduced the concept of self-reflection, and that's why we have called it self-RAG, which along with generating answer, it performs self-reflection as well, where it gonna perform multiple checks of hallucination of whether the answer was relevant or not, whether the document was relevant or not, and then and only then it will gonna produce the answer, and that will increase the chances of providing a high quality response, right? So self-RAG is a strategy for RAG that incorporates self-reflection, self-grading on retrieved documents and generation, and that's what we explained. What we'll learn along with building a self-RAG in this session, the first thing is obviously how to build a self-RAG from scratch. The second thing is how to build a vector store from the knowledge base. So anytime if you are building a retrieval augmented generation system, it is very important to first build a vector store. So whatever knowledge base you have to convert them into a vector store, because the large language models are not very efficient on working on textual data or normal database which humans understand. They are more efficient in with numbers, because these are deep neural networks under the hood. So we convert the knowledge base into the vector stores, which holds the vector embeddings of your knowledge base. So whatever you have in English or Hindi or any other language, it converts it into the vector embeddings and stores them in a vector store, which can be further given to the large language model so that they can understand whatever you have given as a knowledge base, right? The third thing we're gonna understand is how to check for hallucination in your workflow. So how to understand whether the large language model is hallucinating or not. That will also check. Apart from that, we'll also understand how you can evaluate your model's performance in your workflow. So how to understand whether the large language model is providing correct or helpful response and performing correctly, right? We'll also understand that while building self-RAG. So these are the few things, these are the few points we're gonna cover, and we'll see how to implement all of these things from scratch. Okay, so this is the problem statement. Let's move on to the high level design. This is the high level design which I have. I got some empty spaces, so I added a image, but let's focus on the diagram. Let me zoom it out a bit so that okay, this should be all right. Okay, cool. So I hope this is visible. We start from the start and we end at the end, because when you are building agentic workflows in LangGraph, every graph starts from a start node and ends at the end node, and within that you have your business logic incorporated, right? So from after starting, we have a create model. This node creates your large language model. The idea of having it encapsulated within a node is to control the configuration of the model. So if I want, I can, so suppose right now, I guess if a model, suppose if GPT-4 is performing really good for my use case, I can use GPT-4 in this. So the create model, I can configure it to create a GPT-4 model with a given configuration. But what if in future, there is some newer version of some model which can perform even better? Then I don't have to go in every node and change the specification of the model. I can specifically go here at the create model node and I can change the model configuration that will be reflected everywhere in my workflow. So basically whatever other nodes using a large language model, it is using it from the create model. So I create the model instance and configuration once, which is being reused by all the other nodes, so that I have a control over the model configuration. That is the overall idea. So the first and foremost thing, we're gonna create the model. Once the model is created, the second most important thing while building a RAG is to build a vector store. So you should be having a knowledge base on which you want to build your RAG workflow. So what you will do is that we're gonna pick the knowledge base and we're gonna convert them into the vector store, right? And I explained what a vector store is earlier. And we'll see that you don't need to provide your entire content. Instead, if you have knowledge base in the form of links, you can also incorporate that so that you can ground your model on those information. Once you have built the vector store, the third step is to get the relevant documents, because when you have built a vector store, the vector store can be pretty huge, and when a user asks a question, we do not want the model to go to the entire vector store and look for information, because The first thing that can cause some less relevant information or lower quality answers from the model. The second thing is we can max out the context window of the model because there is a limited information we can pass it to the model. So it is important to filter out the documents from the vector store to pick only most relevant document where the probability of the question of the user being answered is very high. So when a user asks a question, we're gonna look into the vector store for the most relevant document where the answer can be for that question, and we pick only those documents and we gonna filter the rest of the documents out. So that's what the get relevant documents does. After that, when we get the relevant document, we give it to the grade document node. Now this is where the self rag or the self reflection concept comes up or is implemented, because when we are grading the document, we get the important document, but we perform a layer of self-reflection where we tell the model that, hey, these are the important documents which I have retrieved from the vector store for a given question. Now what you have to do is that this is the question, these are the documents. Can you tell me that all the chunks of the documents are relevant, or if any of the chunks are irrelevant, you can simply answer with a no, and I'll gonna filter those documents out. So you can think of it as another layer of filtering, a layer of self-reflection on top of your RAG workflow. Once this is done, it will gonna tell you whether you can continue or whether you can end the workflow. This grade document node will tell you to continue if there is some documents which are relevant or which passes the grading system. If even one of the document passes the grading system, it will gonna tell you to continue. If all of the documents were irrelevant, then it will gonna tell you to end the workflow. And this is how you're gonna understand whether the documents were relevant or the self-reflection worked or not. Okay, once the documents are graded, then you generate the answer, because we have a layer of self-reflection, another layer of filtering which filtered the documents. You give this document along with the question to the large language model so that they can generate the answer. Now this will generate the answer. The large language model will generate the answer for you. Now we have one more layer of self-reflection which will check for hallucination. So this node will gonna get the question, will gonna get the relevant documents, and will also get the answer generated by the model, and it will gonna check for the hallucination. If there is no hallucination, it will gonna continue, right? And it will gonna grade the answer. Now this is a third layer of self-reflection where given the answer, we're gonna grade it how helpful it is or how relevant it is. If the answer is not relevant, it will gonna end, and if it is relevant, the answer will be returned. So in the shared state, we have these flag, hallucinated flag and answer relevant flag. If any of these are false, we can understand that our model has hallucinated or our model has not performed well while generating the answer. So you will gonna understand this even more clearly when we'll go ahead in the code walkthrough and when we'll build this self rag from scratch. So the grade answer, as I was saying, the grade answer will gonna grade your answer on the question which was given, and it will gonna tell you that how helpful the answer was generated by the large language model. After this is done, this was the third layer of self-reflection. After this is done, our workflow will end, and by the end of the workflow, you'll get an output which will gonna tell you that whether your model hallucinated, how was the performance, whether the model performed well with the answer generation, and your answer as well returned by the model. And this is what we are building. This is what we are calling it a self rag. So this is the paper which I was talking about, which was also linked in the tutorial of the LangChain repo. So the self-rag, learning to retrieve, generate, and critique through self-reflection. The abstract, you can find the abstract very readable, and despite their remarkable capabilities, large language model often produce responses containing factual inaccuracies due to their sole reliance on the parametric knowledge they encapsulate. Retrieval-augmented generation, an ad hoc approach that augments large language models with retrieval of relevant knowledge, decreases such issues. However, indiscriminately retrying and incorporating a fixed number of retrieved passages, regardless of whether retrieval is necessary or passages are relevant, diminishes language model versatility or can lead to unhelpful response generation, we introduce a new framework called self-reflective retrieval-augmented generation. We also call it self-RAG, that enhances language models quality and factuality through retrieval and self-reflection. And that's what we're gonna build here in this video. We're gonna build a RAG workflow, and on top of that we'll also introduce self-reflection checks or self-reflection nodes, which will gonna make it a self-reflective retrieval augmented generation workflow. Now, this is a pretty intuitive paper, and you can go through it, skim through it. One interesting thing I found out, which you will find very relevant to the thing which we are building here in this video, is this part. This is one of the tables, and they have clearly mentioned what are the checks a self-RAG should have. And the table 1, 4 types of reflection token used in self-RAG. Each type uses self tokens to represent its output values. The bottom 3 rows are the 3 types of critique tokens. You can think of it as a self-reflection layers. And the bold text indicates the most desirable critique tokens. X, Y, D indicate input, output, and a relevant passage respectively. So if I want to simplify it, you can think of X as a question which a user has asked. Y is the answer generated by the large language model, and D is the document or the context which was picked from the knowledge base. These are the 3 XYD parameter. Now the first thing is retrieve. It checks whether you want to retrieve from the relevant document or not by providing yes, no. Is rel is saying the relevant. We will build this reflection layer in our workflow going ahead. It checks for a particular question and the document whether the document was relevant to the question or not. This will be our first self-reflection layer. Second is SUP, meaning is supported, saying that all of the verification worthy statement in Y is supported by D, saying if the model has generated an answer, it is supported by the document, and that is our hallucination grader. That will be our hallucination grader, which will be implementing in our workflow. The third and the last reflection layer is checking for whether the answer is helpful or not, and it has a is use. It is named as is use, saying Y is a useful response to X, meaning if a user has asked a question, I need to go back. Okay, let me skim through it again very quickly. Yeah, so if a user has asked a question, then a model responds with an answer, then whether the answer was useful to the question or not. We're gonna build these 3 reflection layer in this video, in this tutorial, and we'll see how you can build your entire self-reflective retrieval augmented generation workflow. Okay, so this is what the paper is all about. I'll add the link to the paper in the description of this video so you can go through it. And now let's build the workflow. Okay, so now we are doing the code walkthrough. Let me quickly open the graph, and this is how the graph looks like. Let me collapse it. And the first and foremost thing I have done here is I have imported all the libraries. These libraries are open source as always, so you can also do that. Also, the link to this code is like I've uploaded this code on my GitHub profile, and as usual for our rest of the videos as well, we used to have a single repo, that is AI Engineering 101 GitHub repo, which has all the source codes of all the episodes which we have in this AI Engineering 101 playlist. So this will also be added to that repo, and the link to the repo is in the description of this video, so you can head over to that, and you can, it's always I always basically suggest to head over to that code base and go through that code once you have watched the video, or basically you can do that while watching the video as well. If you are stuck at any point, you can go to that code base and you can take a reference, right? And even though when you are building this as a project of yours, you can take the reference from that code base, so that is always helpful. You can get that from the description of this video. And going forward, these are the libraries which we have. All of these are open source, and this is a single Python file, so all of these are incorporated in a single Python file. And we're gonna see how you can build a graph like this. Okay, so the first thing is all the libraries are imported. After that, we have a knowledge base. So for me, I have a knowledge base URL. You can have your files as well. If you have some PDFs or if you have some text file, you have some markdown files, you can give that as well as a knowledge base, and it totally depends upon you what kind of knowledge base you are giving. For the sake of this session, I am giving the knowledge base as the URLs, and these URLs are the newsletters. Basically, I maintain an engineering newsletter called Systems That Scale, and these URLs are the two editions of my newsletter. The first one is on the parallel execution of nodes in an agentic workflow in the LangGraph, and the second is tool calling in LangChain, right? So both of these are related to AI engineering and some optimizations. So once we have this knowledge base and once we build a RAG on top of it, we can ask questions related to that, and we can see how this RAG workflow performs self-reflection, and at the end how it generates the answer. So the first thing is to build a shared state, because I have explained earlier in my previous videos as well, when you are building an agentic workflow in LangGraph, you have to build a shared state first, because any information which is getting passed from one node to another happens through a shared state, and this is as a name suggests, this is shared between all the nodes in your workflow. And even though if you want to give the input to your graph while running it, you give it through the shared state, and the response returned by your graph at the end is also in the form of the shared state. So the fields should be there in the shared state so that you can access them, right? This is how our shared state looks like. The first thing is a question, which is the question which is asked by the user. It's a string. Second is generation, basically the answer generated by the model for that question. It's also a string. Documents, it holds the document which is retrieved from the knowledge base, which is a list because it's a list of documents. Model, for this session we are using the chat OpenAI, or basically the GPT chat models. So that's why I have declared it as a chat OpenAI class. Next we have vector store. We are using Chroma vector store, which is provided by LangChain. So you'll see how you can build a Chroma vector store here in this session. The second thing is hallucinated. It basically stores whether the model hallucinated or not. And valid answer, it tells whether your model, or basically whether the large language model produced valid answer for the question asked or not. So these are the two self-reflection layers which we explained earlier. After that, we have some data models. These are specific data models for different works. One is for grading the document. That was the first reflection layer, where we graded the retrieved documents from the vector store to understand whether the documents were relevant according to the question or not. And all these, like, you can think of this as an output structure. So we are telling the large language model to output in this class format, where the model will output with a binary score, and the binary score should either be yes or no, as the description says. So this description will be available to the model so that they can understand what should be in the binary score. And it says documents are relevant to the question, yes or no. So if the model returns with a yes, meaning the documents are relevant to the question and you do not need to filter them out. If they say no, then it means that the document was irrelevant and you can filter them out. This is also another data model for grading hallucinations. So it is very similar to the first one as well. The only thing is it tells you whether the model hallucinated or not. It also returns the binary score. The description is answer is grounded in the facts, yes or no. Then the third one is grade answer. It is also similar to the previous base class. It tells you whether the answer generated by the large language model addresses the question or not, or basically solves the question or not. If it does, then you can return yes, otherwise you can return no. So all of these are the three layers of self-reflection which we are building on top of our RAG workflow, and that's why these are required. We'll see how we'll integrate this in our workflow moving ahead. Now I don't have any utility method, so I can simply remove it just to clean this. And now we'll discuss the nodes which we have in our workflow. We have already looked these nodes at a very high level in the design. you can see these nodes being implemented here. The first one was create model. I already explained what create model is. It basically creates a model which will be used everywhere in the workflow. I am creating a chat OpenAI model which I am creating a GPT-4o mini. Currently the temperature is 0, but you can set other configuration if you want, and that will be respected all around your workflow. So that is one of the benefit we get while putting it in a separate node. And you can see once we have created the model, we have set the model in the shared state, or basically we have saved the model in the shared state. And you should know the reason, because once we have saved this in the shared state, we can use this in the future nodes. So wherever in future we are trying to call the large language model, we can pick the model from the shared state because we are saving it here. After that, we return the state. You should know that every node in a LangGraph in your agentic workflow takes in a shared state and return the shared state. And that's how these nodes communicate to each other. Now the second one is building a vector store. Now we already saw this node in the design. What it does is that when you give a knowledge base, it extracts the document from your knowledge base URL. It splits those document and convert those document into vector embeddings. Once your documents are transformed into the vector embedding, it stores in a vector store, and then it returns the vector store so that in future you can retrieve from the vector store. So you can think of vector store has all the information of your knowledge base, and then when a user asks a question, you can retrieve the relevant documents based on that question from that vector store. So that's why we need to build a vector store. Now the first thing it does is that for all the URL present in our knowledge base URLs, remember we gave 2 URLs as a knowledge base for 2 of our editions of the newsletter. It uses web-based loader. That's also an open source library provided by LangChain. And what it does is that it extracts the content for the given URL. So whatever URL I have given, it will gonna extract the content. So the URL was the article, the URL of the article. So basically it will extract the content of the article from the URL, and it will gonna put them in the documents. Now we're gonna iterate over the document, and we're gonna convert the document, or basically we're gonna split the documents, right? So here is the docs. For all the sublist in the docs, it looks for all the item within the sublist. So what it does is basically you can think of it as we have a big document, it splits it into multiple small document or small chunks so that you can convert them into embeddings and store them in a vector store. Once you have a list of the document, you can use the model of your own to convert or to split them, right? And once this has been split, you can store the document splits here. So we have initialized our own text splitter where we are deciding how many chunks each document should have. So you can think both of these as splitting your documents. The first one is splitting it with a new line, or if there is any separate list of documents, it is storing it here. But after that, you're specifying a chunk. So basically you're strictly saying that, hey, I want one chunk of document, not more than size of 250. So perform more splitting and split the document so that every chunk has a size of 250 and the chunk shouldn't overlap, right? So this is how I am constructing my splitter, and then with this splitter I am splitting the list of the documents which I have. So it further split the documents into the doc splits, right? And this will gonna give you the list of the documents as explained, as described here in the method. And this doc splits now will have a list of the documents. It will basically have a list of documents of your knowledge base, and it represents your knowledge base. Now what you can do is that you can store them in your vector store. Now for that I can use Chroma. It is also provided by LangChain, and what it does is that it only takes the split, your document split, or basically the list of the documents, and you can give the embedding. So basically you have to provide the embedding. There are different ways you can convert your text document into embedding, and I am giving the OpenAI embedding, so it will use the OpenAI embeddings to convert your documents into the vector embeddings, and then it will store that in your vector store. So this will build your vector store. So you can think of this method taking your knowledge base and converting them into the vector store. So basically it takes the knowledge base, convert them into vector embeddings, stores those embeddings in a vector store, and then it will gonna return that to you. Once the vector store is available, we can store that in our shared state. Now again, this is very important because we want to use the vector store in the future nodes going ahead, and that is why we are storing it, we are saving the vector store in our shared state so that we can reuse it later. So we save that in our shared state here. This line does that, and after that it will return the state. Now this is how we build the vector store. Now once we build the vector store, we can get the relevant documents, because now you have the vector store. So what you can do is that you can build the relevant documents, or basically you can fetch the relevant documents from that vector store. In order to fetch the relevant document, you need to have a question. So when a user asks a question, you need to go to the vector store and you need to pick all the relevant documents on the by checking the question, and you pick the all relevant documents where you think that the probability of having an answer is really high. And this is what it does. It's a small method. It simply takes the question from the shared state, because remember I mentioned that even if you want to give some input to your workflow, you need to give that as a part of a shared state. So if a user wants to ask a question to your RAG workflow, we'll give it as a part of a shared state. So we pull the question from the shared state and we get the relevant document passing that question. So from the vector store, there is a method of get relevant documents. So that's what that's how the Chroma vector store simplify things for you. You don't have to perform any mathematical calculation to understand how a particular document or vector chunk is relevant to a question. Chroma vector store does that for you. So it has a method get relevant documents where you can simply give your question and it will gonna return the relevant documents to you. Now this is how you do things in RAG while building a RAG workflow. Once you have the document, you can, as usual, save that in our shared state, because we want to utilize these documents later. So what this method does, this method get the relevant documents depending upon the question which the user has asked from the vector store which we built earlier, and this document is now saved in the shared state and the shared state is returned. This is what this method does. Now another thing what we want to do is to introduce a layer of self-reflection. So we got the relevant documents from the vector store. Now we will perform another layer of self-reflection where we'll see that whether these documents were relevant to the question asked or not. And this is how it is done in the grade documents method. It says determine whether the relevant documents are relevant to the question or not. These are the documents which we extracted from the vector store and saved in the shared state. Now you can I can skip the documentation of the method here and I can directly move on to the logic. So the first part of the logic basically extracts the documents. So we have a question, we get the question from the shared state, we get the documents from the shared state, and we build a structured LLM grader which uses the model, but this is the model which we are getting from the shared state because we have a node earlier which creates the model and saved it in the shared state. So you can use that model. On top of that model, on top of our large language model, we have called a with structured output method which instructs the model to return the output in a structured format, and the structure is given here in the grade document. So this was one of the base class which we described earlier. It has a binary score field which tells the model to respond in a yes or no format. And basically what with this line we are telling that our basic model to respond in a structured way, and we are telling them what the structure of your output should be, and we are calling that as a structured LLM grader. Now if you invoke this with your question, it will gonna answer it in the format of the structured output which you have given. Once we build our structured LLM grader, we can build our prompt. So the prompt tells the large language model to grade the document on the basis of the question. So we are passing the document and we are passing the question here in the prompt. Along with that, we have a document grader prompt which I have described, which I have saved in another file, a prompts file. So I can click on it and I can go to the file here. So this file has all my prompts. So I have 3 layers of self-reflection, and for that I have 3 grader prompts. For the first layer of self-reflection, the document grader prompt, this is what it says. You are a grader assessing relevance of a retrieved document to a user question. It does not need to be a stringent test. The goal is to filter out erroneous retrievals. If the document contains keywords or semantic meaning related to the user question, grade it as relevant. Give a binary score yes or no to indicate whether the document is relevant to the question. A very straightforward prompt. Now I can come back. So this was the document grader prompt. Along with the prompt, I have also given the document and the question for the model to perform a self reflection, and then I can pipe all these things together. So we give the prompt and we give the prompt to the structured LLM grader, and we expect the response, the structured response, as a binary score of yes or no. Now this retrieval grader, I can invoke this for each and every document. Now the idea is to get all the documents. So remember, we stored, we get the documents from the vector store, and we called the get relevant documents on the vector store. That will give you the list of relevant documents. Now we iterate on those list of the relevant document, and for every document on that relevant list, we check for the relevance of those documents. So we invoke this retrieval grader which we have defined on each and every document present in the list. And what we do is that it's a simple for loop, and we pass the content of that document along with the question. Right, we pass the content of the document along with the question, and we get the response of the grader. Now if the response, now remember, we have we have instructed the large language model to return the response in a format, and that was a field binary score which is yes or no. So the model will respond in that format. So the response will have a binary score field, and that can be yes or no. So we are saving that grade here, and if the model has responded with yes, meaning the graded document or the document which we just graded was relevant, and we can append that in our filter documents. If the graded document was not relevant, we can continue. And after that, once this loop is done, this filter document list, which was initially empty, will have some relevant documents which we are adding here. Okay, and then we can update the list of the documents. So initially we had all the documents which was returned by the vector store, all the relevant documents which was returned by the vector store. What we did after that, we performed another layer of self-reflection where we filtered the document on the basis of the relevance of the question. And once that filtering was done, we update the document with the filter document, and we save that in the shared state, and then we return the state. So now our list of the documents are updated with the filter documents, which was done as a part of the first layer of self-reflection. Now remember, when we are going through our high-level design, we discussed that when we called the grade document or when we graded the document, we can actually decide to exit, or we can continue our RAG or our self-RAG workflow. It all depends upon whether the filter documents were present or not. So if here for every document the score was no, then our filter documents list will be empty, and hence in the shared state the list of the documents will be empty, meaning that we don't have any relevant documents. So the self-reflection layer said that you don't have any relevant document and there is no point of going forward, right? So we'll introduce a conditional edge in our workflow which will take this decision, because we have saved the updated documents in our shared state. So it is feasible to build a conditional edge, and this is how the conditional edge looks like. It's another definition which is decide to generate. It is a very simple conditional edge which takes the question, or which basically take the filter documents, and I think I can remove this. Okay, which takes the filter documents which was filtered as a first layer of self-reflection, and it checks whether there was something in the filter documents or not. If there was nothing in the filter document, we can print all documents are not relevant to the question, and instead of transform query we can say that end, right? So decision all documents are not relevant to the question, end, meaning we'll return an end string telling the workflow to end the workflow and return it back to the user, so that user can understand that there was no filter document for the question. Otherwise, if there was something in the filter documents, we can continue to generate and will print the decision, generate, and will return continue, which will tell the workflow to continue. Now we're gonna place this conditional edge when we are building the graph, and we'll see how this conditional edge gives the output and how you can use that to redirect your control flow of your agentic graph. Now after that, if we decided to go ahead, if there was some filter documents, then we continue and we generate the answer. Now here we're gonna generate the answer. We're gonna tell the large language model to generate the answer because the first layer of self-reflection is done and we have some filter documents. So we get the prompt and we tell the LangChain to build the prompt, or basically to direct the prompt to the model. This is the model which we have saved earlier in the shared state, and we have the string output parser which is telling the model to return the output in the form of string. So basically we are expecting only the answer in the form of string from the model. This is a LangChain which we have built. It's a piped chain of the prompts, the model, and the output format. We can invoke the document and the question in this LangChain, and we can expect an answer. Now the prompt, we are pulling the prompt from the LangChain hub. Now this is one of the standard RAG prompt which tells the model to return an answer on the basis of a given context for a question, right? So this you can get this you can pull this prompt instead of defining your own prompt for a basic RAG, you can pull this prompt from here, and then you only need to pass the context and the question. The context was the filter documents and the question was the user question which we picked from the shared state, and you can expect an answer from the model. And whatever model has generated, we can save that in our shared state, in the generation state, right? And this will gonna save the answer of the large language model, and it will return the shared state for the future self-reflection layers. Like so, the prompt which we pulled from the LangChain hub, this is how the prompt looks like actually. It says you're an assistant for a question answering task. Use the following piece of retrieved context to answer the question. If you don't know the answer, just say that you don't know. Use 3 sentences maximum and keep the answer concise. It has a placeholder for placing your question, it has a placeholder for placing your context, and it has a placeholder for the answer. So what you can do is that you can put your question here, you can put your context, which in our case was the filter documents here, and then you can expect an answer from the model. So this is a pre-built prompt which is available in the hub, and instead of declaring all of these in your prompt folder or in your constant directory and maintaining it, you can directly pull this prompt template from the hub, and you can use that for your RAG workflow. So now once you have generated your answer, it is the time for the rest of the 2 self-reflection layer. One was to check for hallucination and another one was to check for the quality of the model response or quality of the answer generated by the model, by understanding whether that answer answered or answered the question asked by the user or not, right? Or basically addressed the question answered by the user or not. So the first method is check for hallucination. This will gonna check for hallucination by the model. And what we have, remember in the shared state, we have a hallucination flag. So this method will gonna flip that flag to true if there is a hallucination in the answer generated by the model. If there is no hallucination, it will gonna let the workflow run without flipping that flag. So in order to do that, first need to get the documents and get the answer generated by the model from the shared state, because we have saved both of the things in our state. We have a structured LLM grader. It is very similar to the one which we defined earlier. The only difference is we get the model from the shared state. We get the large language model from the shared state. This is very similar to what we did. The only difference is the structured output which we are giving it to it. Instead of giving the grade documents, we are giving grade hallucinations, which also has a similar structure. It also expect a binary score field which can be either yes or no. Now once we have this grader, basically we are asking the model to respond in a particular format. Once we have this grader, we can ask the chat prompt template, or we can build the entire prompt. The first thing is the hallucination grader prompt, which I have saved it in my prompt directory, and along with that I am giving the document and I am also giving the answer generated by the model, and then I can expect a score, whether it's a yes or no, from the large language model. Now the hallucination grader, I can pipe the hallucination prompt and I can pass that prompt to the structured LLM grader, which can return the response in a structured format, which has a binary field or a binary score of yes or no, right? And while invoking, I can set the documents and I can set the generation or the answer generated by the large language model, and then I can return the and I can get the score and I can check what the grade was. Now before going forward, let's quickly understand the hallucination grader prompt. This is also a very small prompt. You are a grader assessing whether an LLM generation is grounded in or supported by a set of retrieved facts. Give a binary score yes or no. Yes means that the answer is grounded in or supported by the set of the facts. So basically we are telling the model that, hey, these are the documents and these are the answer generated. Can you tell that whether the answer that was generated was based on the document which is provided? Now this will check for the hallucination. This will gonna check that whether the model is answering according to the knowledge base or on the basis of the knowledge base which you have given, or it is like going away and answering it on its own training which it has done, right? This is what a hallucination grader does. Now once you have built the hallucination prompt, you can pass it through the structured LLM grader and you can build a hallucination grader which you can invoke with the document and the answer generated by the large language model, and you can get the binary score. Now the binary score can be yes or no because we have defined that in our base class, the grade hallucinations class, right? And the grade can be yes or no. So if a grade is a yes, it means that there was no hallucination. So we have printed decision no hallucination, generation is grounded in documents, and we do not flip the flag. So we set the hallucinated flag to false, saying that there was no hallucination in the model observed. If the grade is not yes, then we say that model hallucinated, generation is not grounded in documents, and we flip the hallucinated flag to true, so that once the workflow is done and once the shared state is returned to the user will know from this flag or by checking the flag that whether my model hallucinated while answering or not. Now once you have checked for the hallucination, it is time to grade the answer. So the 2 layers of self-reflection is done. It's time for the third and the last layer of self-reflection, where we check that whether the LLM generated relevant answers or not. Now this is the method which will do it for you. It's also a very similar method to the hallucination grader. We'll get the question and we'll get the answer generated. So in the hallucination grader, we were checking the document and the answer generated, and we were checking their relevance. Here we are checking the question and the answer generated to understand their relevance. Along like the way we did earlier, we are building the structured LLM grader, which is getting the model from the shared state, along with the structured output, which is now the grade answer base class. We have gone through all these 3 base classes earlier. So grade answer base class is also a similar base class which will have a binary score field which can have a value of yes or no. Now along with that, I have the chat prompt template where I will have an answer grade prompt. This prompt is also present in my prompt file. Along with that, we'll give the question and the answer generated by the model along with this prompt, and we can expect this answer prompt. We can pass this prompt to the structured LLM grader and we can expect a response in the form of a structured output which will have a binary score field that can be yes or no, right? And then once I have built the grader, I can invoke this with the question and the answer generation, right? And as usual, I'll expect the score in yes or no. Okay, now let's quickly understand the answer grader prompt. I can go back here, and this is the answer grader prompt. It is also a very small prompt. You are a grader assessing whether an answer addresses or resolves a question. Give a binary score yes or no. Yes means that the answer resolves the question. So your model will respond with a yes if the answer was relevant to the question. And we get this grade from the binary score. So the model responded in a structured format, and we get the binary score field from the response, and we saved it in the grade. Now the grade can be yes or no depending upon the output. If the grade is yes, meaning the answer was, or the answer addressed the question or resolved the question, and hence we flip the valid answer flag to true. Otherwise, the generation did not or does not answer, does not address the question, and we flip the valid answer flag to false. Now this is also present in the shared state, and once this node is done, it will gonna flip the valid answer field depending upon whether the generation was helpful or not. So if the generation was helpful, the valid answer flag will have true, and you can understand that okay, my model generated the valid answer. If the valid answer is false, you will have the idea that okay, the answer generated by the model was not valid, and hence you can take your next step as like however you want, and then you can return the state, or basically this node returns the state. Now this is all the nodes, these are all the nodes which you will have in our self RAG workflow. And now we're gonna see how you can arrange these nodes when you are building a graph so that they can perform the way we want. This is done in the build graph method. We have built agentic workflows in LangGraph before as well, and we used to build this graph. So the building the graph is divided into 3 steps. First is defining the nodes. Second is adding the edges between the nodes so that you can build the graph, and the third one is compiling that build graph, right? So the first thing in the build graph is adding the node. All the node which we have defined earlier, all of these are added here. Once the nodes are added, we build the graph by adding the edges. Now we have seen the design of the workflow, and we are building the workflow in the same order of the design. So we start with the start node. We go to the create model. Once the model is created, we build the vector store. Once the vector store is built, we get the relevant documents. Once we get the relevant documents, we go to the first layer of self-reflection where we grade those documents. Once the documents are graded and filtered, then we decide to generate. This was one of the conditional edge which we saw earlier, which returns either continue or end. Continue means we have some relevant documents filtered out by the grade document method, the first self-reflection layer, and if it says continue, we can generate the answer. If it says end, meaning there is no filter document, we can end. After that, if it goes to generate the answer, we can generate the answer. We can let the large language model generate the answer, and then we can check for hallucination. After checking for hallucination, we can check the graded answer, or basically we can grade the answer, telling whether the answer resolved the question or not. And once everything is done, we can end the graph. So once this is done, we can compile, right? We can compile the workflow, and or basically we can compile our graph and we can return. So this build graph will gonna do everything for you, and will give you a graph which you can invoke. And once you can invoke that with your question, and you can see all of these things happening in action in a sequential fashion, right? And then we can see how you can run your graph. Now after that, there is a simple block of code which runs the graph for us. So first we load the environment variables, then we call the build graph method, which builds the graph by adding the nodes and adding the edges between them, and then compiling it and returning the graph. So whatever we have done above, it builds all of it and it returns you a graph. Now you can invoke the graph. I mentioned earlier that every graph or every agentic workflow built on LangGraph takes a shared state as an input and gives the same shared state as an output. So while invoking, I will give a shared state, and initially I don't have much to put in my shared state. I only have a question, which is what is tool calling. Now it is one of a relevant question from my knowledge base, because one of the article was on tool calling, which I have added in the knowledge base, if you remember. So this question should be answered correctly, right? Now I can invoke the graph and I can try to get the response. Once I get the final response, I can check. So once this graph is done, I'll get a response and I can check for hallucination and answer validity. So you remember 2 flags which we set in the hallucination grader and grade answer nodes. So these are the two flags. If the hallucinated flag was set to true, meaning the model hallucinated and the generation is not grounded in the document. So we can print it to tell the user that hey, the model has hallucinated. Second flag was valid answer. If the valid answer flag was false, meaning that the answer is not valid or basically the answer does not resolve the question, then we can print this. The answer is not valid for the question. If none of these are printed, then we can have the idea that okay, the answer was valid, and at the end we can print the answer which was generated by the model. And this is what the entire graph or this entire agent graph is all about. Now what we can do is that we can run this graph to understand how it will gonna perform. So now it is time to run the workflow which we have built. So it is the action time where we see whatever we have gone through is being executed correctly or not. Now the question which I have asked, that what is tool calling, and that question is one of the question which should be answered from the knowledge base, so the model should be able to answer without any hallucination, right? So what I can do is that I can run my file. So this Python agent graph file, I can run it like this, and then I can see things in action. So it created the GPT model, it built the vector store. Now it is on the next step. It retrieved the relevant document. It is checking whether the documents are graded correctly, and the grader sets that says multiple documents are relevant, meaning that the documents which was retrieved by the vector store was graded or were relevant to the question asked, and hence the decision was to generate. And once the generation was done, the hallucination check was performed, and it says no hallucination, generation is grounded in the documents, as obvious because we asked a relevant question. And then another check was generated answer relevance, decision generation addresses question, meaning the answer which was generated resolved the question. So the three layers of self-reflection passed. The first layer was this one, which graded the documents. The second layer was this one, which checked the hallucination, and the third layer checked for the relevance of the answer. All these three layers passed and we got the final response. Now this is how the final response looks like. Tool calling is a concept in LangChain where large language model interpret human messages and determine which tool to invoke based on the context. These tools can include APIs, functions, or databases, allowing the AI model to perform a specific task with the appropriate parameters. Essentially, it enhances the AI's ability to execute operation by leveraging external tools effectively. Now, this is answered from my knowledge base. Now what you can do is that you can maybe have your own knowledge base. Maybe it might be some personal data which you don't want to like put on the internet. So you can train your model on top of these data, and you can ask questions on top of it, and you can maybe build your own self RAG which performs some self-reflection on top of your RAG workflow. Now we have run the workflow, and we have understood how the model or how the workflow will return responses for relevant questions, but we have introduced some self-reflection layers, and it is very important to understand whether these self-reflection layers are able to detect anomalies or not. And to test that, I am adding a question which is totally irrelevant of the knowledge base. So in the knowledge base, I have given two articles, which one of them I guess was on tool calling, another one was on parallel execution, and both are basically in the AI engineering domain. And the question I am asking is totally out of the AI engineering domain. I am asking what is a disjoint set data structure. Now, once I give this question, what should happen is that the first self-reflection layer that grades the documents should come up with a response, or basically should declare all the documents to be faulty, or basically all the documents are irrelevant, and hence we shouldn't go ahead with the graph, right? That's how we build the graph, or that's how we build the first reflection layer. Now once we do that, our model will end, or basically our graph will end at that point of time when we are not able to get any filtered documents after the document grader reflection layer, and in that case we'll not have these in our keys. So if you'll directly print for response hallucinated, your the execution will gonna abruptly end with the error. Python will give you error. So in order to resolve that, or basically have a workaround, we are first checking whether that key is present in our shared state or not. If the key is not present, then there is no way of checking what the value of that key is. And I'm doing the same thing for all the cases so that we don't end up terminating the control flow abruptly, right? So basically none of these will be printed, because the nodes going forward for generation, hallucination, and checking the answer validity will not be run, because we don't have any documents in the first place. And this will all be done with the help of the conditional edge, because in the conditional edge, when the documents are graded and when we go to the decide to generate conditional edge, it will gonna return with the end, because there was no filter documents, and our workflow will end at that point of time, meaning we'll not be able to run the generate answer, check for hallucination, or the grade answer nodes, and hence there is no point of checking all these. So we are adding a initial check so that we don't end up ending the or abruptly stopping the script, right? So now this is done. I am asking a very irrelevant question. Now let's try to run this. Let's try to see how will it perform. So I can again run my agent, and this will gonna create the GPT model, build the vector store, and once that, it will gonna retrieve the relevant documents, and you can see the grader is performing or providing their output saying documents not relevant, document not relevant. So all the documents which it has tried to check, all of them are irrelevant, and hence it is assessing as a final decision that all documents are not relevant to the question, and hence it will gonna end, and then there is no final response. And this was all done by our self-reflection layer, and that's where self-RAG stands out. It will gonna save you from all these issues. Like if in future your model is hallucinating, if the answer was not relevant to the question, if the question was not at all relevant to the topic on which you are building a RAG workflow, your self-RAG workflow will save you from all of this by having a self-reflection check. Now this is what we build. So this was the end of this session. We actually built a self-RAG from scratch based on the research paper titled Self-RAG: Learning to Retrieve, Generate, and Critique Through Self-Reflection. So now you understand what a self-reflection layer is and how you can introduce it on top of your RAG workflow. This is the end of this video, and this is a part of the AI Engineering 101 playlist. You can check out more of these videos and tutorials in the playlist. And yeah, if you found it helpful, share it with others, and do subscribe to this channel, and I'll meet you in the next video.